Before solving linear systems, we need to build up our toolbox. We're used to thinking about elements of Rn as being points, but we can also think of them as being arrows beginning at the origin. For example, let's take a look at the element 3, 2, which I'll highlight in yellow at the point 3 units along the x-axis and 2 units along the y-axis. As an arrow, we draw the line from the origin to the yellow dot. The arrow is what we'll call a vector. It'll be distinguished from a point by using square brackets, and we often also write it as a column. So vectors can be added together, and algebraically the way that we do this is by adding across rows, component by component. Geometrically, if we plot -1, 1, then when we add it to 3, 2, we place that vector at the head of 3, 2. Their sum is that arrow starting at the origin pointing at the same place. You should convince yourself that if we had done this the other way, by drawing 3, 2 at the head of -1, 1, then we would have gotten the same answer. Now the other thing that we can do is we can multiply vectors by a real number. This is done by multiplying each component of the vector by the real number. Geometrically, this amounts to scaling the vector, and or reflecting it in both axes if the real number is negative. Now the whole reason that we're doing this is because solutions to linear systems will be modeled as vectors, and we'll see that these operations are useful in that context. Now closely related to vectors are matrices, and an m by n matrix is a rectangular box consisting of the numbers arranged in m rows and in n columns. So for example, I'll write down a random 3 by 3 matrix here. Notice that it has 9 elements arranged in 3 rows and 3 columns. But matrices don't have to be square. We could have done a 3 by 2 matrix. So hopefully you've noticed that vectors are just special cases of matrices. So for example, our column vectors were n by 1 matrices, and while most of our vectors will be column vectors, a 1 by n matrix is indeed also called a row vector. Now just like vectors, we can add matrices, but only if they are exactly the same size. So I'm going to write down 2 random 3 by 2 matrices here. And when we add them, we're going to do it component by component. So I'll extend this step here so you can see how it's done, but normally we can just jump to this last step. And again, like vectors, matrices can be multiplied by a real number. And this is again done just component by component. So in this case, every element of the matrix is going to be multiplied by -4. Now I'm about to copy in a bunch of properties of matrices. These are going to look obvious, but we'll later see that matrix operations aren't always so intuitive. So I can't stress enough that unless you've explicitly been told that a matrix identity holds, you cannot assume it to be true. So take a second, pause the video, and stare at these identities. Convince yourself that they all should be true. Alright, so let's do an example. Suppose that A is this nice 2 by 2 matrix, and I ask you to compute this large, complicated sum. Now, you can compute each of these terms separately and add them together, but let's use property 6. And property 6 says that scalar multiplication expands across addition, or for our purposes, if the matrix is common, it can be factored out. So let's begin by rewriting this by factoring out the A matrix, and for good form, I'll just repeat the question statement. And now I'm going to factor out that A term. Now the thing in the brackets is just a real number, and you can work that out to be 15/16, so we're going to multiply that into everything in our matrix, and it gives us this. And to tidy things up a bit, I'm actually going to pull that fraction out of the matrix, though that's not necessary. And there you go. You now know the basics of vectors and matrices.